Welcome to today's Explainer. We're diving into something pretty wild today, how computers literally trap reality. I'm talking about taking continuous, real-world analog stuff like a sound wave or a massive landscape and translating all of it into digital data. We're going to uncover the mechanics behind this digital translation, get into the specific math and formulas you need to calculate the exact size of that data, and look at how we shrink it all down so our hard drives don't just instantly overflow.
Here's our roadmap for this explainer. We'll start with capturing sound and images, then move to calculating digital file sizes. After that, we'll look at lossy compression with MP3 and MP4, followed by lossless compression using RLE, and finally, we'll wrap things up by conquering a couple of tricky exam questions.
All right, let's jump straight into Section 1, capturing sound and images, or as I like to call it, trapping reality inside a computer.
To really get this, we have to fundamentally understand how analog realities are actually digitized because, the real world doesn't operate in binary ones and zeros. It's continuous. So how does a computer actually capture that? Well, let's look at sound first. Sound waves are constantly varying. To store a wave in a computer, we have to measure its amplitude at very specific, regular time intervals. This process is what we call sampling, and the number of samples we take per second is the sampling rate, which is measured in hertz. Now, every time we measure that amplitude, we have to assign it a binary value. The number of bits we use to represent the amplitude of each sample, that's our sampling resolution, sometimes called bit depth. Now, images work in a really similar way, but in physical space rather than time. A continuous visual is basically mapped onto a 2D matrix of tiny picture elements, which we all know as pixels. The total number of pixels that make up the entire image is known as the image resolution.
And you can really see how a high image resolution captures reality beautifully. Look closely at the curves on this car wheel. Because this visual uses a massive number of pixels that are packed incredibly tightly together, the curves look perfectly smooth. The reflections are super crisp, and the detail is just phenomenal. The computer simply has enough data points to faithfully recreate the original, continuous visual.
But watch what happens if we drastically drop that number of pixels. Suddenly, the wheel becomes fuzzy, blocky, and completely pixelated. There just isn't enough data or enough individual picture elements to represent the image smoothly anymore. So the computer is essentially forced to draw the visual using these large, chunky blocks of single colors.
Which brings us right to Section 2, calculating digital file sizes. This is really all about the cost of quality. Because, of course, capturing high-quality digital data with those massive sample rates and ultra-high image resolutions creates a very real physical problem for us. Huge file sizes that will absolutely chew through our computer's storage space. So how do we actually calculate that cost? Let's break down the math for images into a few bite-sized steps. To find the size of a bitmap image file, you always start by finding the total number of pixels. Just multiply the width by the height. Easy enough, right? Next, you take that total and multiply it by the color depth, which, remember, is just the number of bits used to represent the color of a single pixel. A 24-bit color depth, for instance, allows for over 16 million unique colors. Finally, since your answer right now is in bits, you just divide the whole thing by 8 to find the total bytes because there are exactly 8 bits in a single byte.
For a sound file, the formula is honestly very similar, but we're dealing with time instead of a 2D grid. First, you multiply the sample rate, those samples per second, by the sampling resolution, which is the bits per sample. Then, you multiply that result by the total length of the track in seconds. And here's a crucial detail. If the audio is recorded in stereo, meaning it has two separate audio channels for left and right speakers, you absolutely have to multiply your entire result by 2. Then, to convert that final number into bytes, you just divide by 8, exactly like we did with the image file.
When you do this math, you'll see that just a handful of high-quality uncompressed files can quickly balloon into literally astronomical numbers. Take a look at this massive 68 billion byte figure. That represents a standard 64 gigabyte memory stick you might just grab at the store. When calculating memory in the IEC binary system, 1 gigabyte is 1,024 megabytes, which cascades all the way down to give us exactly 68,719,476,736 bytes. High quality eats through those billions way faster than you think.
So how do we fix that? Let's get into Section 3, lossy compression, specifically MP3 and MP4, and how we trim the excess.
To save our hard drives, SSDs, and network bandwidth from filling up instantly, we rely heavily on data compression. We're going to start by looking at lossy techniques. This is where unneeded data is permanently eliminated. Two of the most famous lossy formats are MP3 and MP4. An MP3 algorithm can compress audio files by up to 90%. How does it do that? Well, it actually cleverly targets the flaws in human biology. It permanently discards sounds that the human ear simply cannot perceive. We're talking frequencies outside our natural hearing range, or softer noises that are masked by louder overlapping sounds. It's a really neat trick known as perceptual music shaping. MP4, on the other hand, works using similar lossy principles, but it goes way beyond just audio. MP4 handles entire multimedia files, which allows for the compressed storage and streaming of videos, photos, and animations all together, while still maintaining a really acceptable quality for things like streaming movies over the internet.
Moving on to Section 4, Lossless Compression, specifically RLE, because sometimes shrinking without losing is exactly what we need to do.
See, there are times we absolutely cannot afford to lose a single piece of original data. If you're compressing a text document or code for a computer application, a lossy algorithm would completely destroy it. This is where lossless compression like run-length encoding, or RLE, comes in to save the day. A great analogy for RLE is thinking about how you'd write a grocery list. Take a look at the raw string of characters on screen. Instead of writing out a string of identical adjacent data like apple, 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 RLE uses an indicator value to simply say 3 apples. In our example, we have 5 A's, 4 B's, 2 C's, and 5 D's. In RLE format, assuming we're using standard ASCII code where the letter A is represented by the number 97, this translates to 0597, literally 5 instances of character 97. It then just continues down the line, 0498, 0299, and 05100. This technique is brilliant because it's completely reversible, and in this specific case, it cuts the required storage space for our text string exactly in half.
All right, let's wrap this up with Section 5, Conquering the Exam Questions. It's time to put all this knowledge into action. Applying everything we've covered to actual exam questions is kind of the final boss of today's explainer. Let's tackle question 1BIII from the Cambridge curriculum. We're given an image resolution of 16,384 by 512 pixels, but notice it says 256 colors. It does not explicitly give us the color depth in bits. And here is the real trick to this question. You have to realize that to represent 256 different colors, you need exactly 8 bits. Why? Because 2 to the power of 8 equals 256. So, boom, our color depth is 8 bits per pixel.
Now we just follow our progressive math steps from earlier. Step 1, multiply the width and height dimensions to get our total pixel count, which is 8,388,608 pixels. Next up, we multiply that by our 8-bit depth to get the total bits, and then immediately divide by 8 to get the total bytes. Now, conveniently enough, multiplying and dividing by 8 just cancels that entirely, leaving us with exactly 8,388,608 bytes. Finally, to convert those bytes all the way up to gigabytes, we have to divide by 1024 3 separate times, once for kilobytes, once for megabytes, and once for gigabytes. The final precise answer you'd write down is 0.007812 gigabytes.
Okay, for our second exam challenge, question 2CII. We need to prove we actually understand the methodology of converting a visual grid of pixels into an RLE-coded format, rather than just doing it with text. Imagine you're looking at a single row of pixels in a simple black and white image, where the gray squares have a code value of 0 and the white squares have a code value of 1.
Just like we summarized that text string earlier, you simply count the repeating visual units from left to right. Let's say we have a run of 9 white pixels followed immediately by 6 black pixels. First, mentally block this as 9 white, 6 black. Then, we substitute in our code values. Again, 1 for white and 0 for black. So this visual seamlessly compresses into the data pairs 9-1 and 6-0. The first number in the pair is the run length, how many pixels there are, and the second number is the actual pixel color code. It's incredibly elegant, super efficient, and best of all, completely lossless.
So now that you know the hidden math behind how we digitally translate reality, take a quick look at your own phone. Think about all those high-resolution photos, the completely uncompressed audio files, and the looping 4K videos you've got saved. Consider just how much invisible, totally redundant data you're carrying around every single day. And think about how many billions of bytes your phone's processor is tirelessly compressing and decompressing behind the scenes just so you can scroll smoothly. It really puts the whole battle of the bytes into perspective, doesn't it?